Hello students, how are you all? So in this video we will be talking about some of the very important questions from the rotational mechanics, one of the very important chapters from class 11 physics. So the purpose of this question is just to give you some idea from the J advanced and mains type of questions. So NEET students also can go through these questions, but yeah, some part of the questions would be important. Not all of the questions would be important for the NEET point of view. But if you are in class 11th, obviously you can go through these questions either JEE, either you are planning for JEE or NEET, doesn't matter. Okay, so let's just start the question. So the first question, okay. So the first question says that we have a sphere of mass m which is placed on a plank. Okay, so sphere given some angular velocity. So sphere is already rotating, and that rotating angular like it's rotating like this, means it has angular velocity. Okay, and we are placing it on the plank. There is a friction coefficient between the sphere and the plank, mu, and the ground is there. So the ground is smooth. So the question is asking that the initial acceleration of the sphere relative to the plank will be. Acceleration of sphere we need to find with respect to what? Plank. So let's see. We'll draw the free body diagram of the sphere. Forward we have what? A. At the contact point there would be friction. That friction would be mu into normal, because obviously in the start there would be a slipping between them. So this friction is which one? Kinetic friction. So mu into normal, mu in mg. Same friction on this one, backward, mu mg. So you can write down the acceleration of this one, force by mass, mu g, and acceleration of the plank. So force, mu mg, mass of the plank is also m. Okay, so both here sphere and mass plank both are of same mass. So acceleration would be here how much? Mu g. Now the question is saying that we need the relative acceleration of the sphere relative to what? Plank. So we know how to calculate the relative concept. So I will sit on the plank. Whatever acceleration it has, it would be given to the sphere. So sphere has how much acceleration? Mu g. Plank has how much acceleration? Mu g. And I would sit on the plank, give the acceleration backward to the sphere. So net acceleration of the sphere would become how much? 2 mu g forward. Got it? Okay, no problem in this question. Okay, so let's see the next question. Question number 2. We have this arrangement of rod, both are equal L length. The question is saying that angle theta in equilibrium, when this rod is hanging such that it is making equilibrium, so what would be the angle theta in that case? So in the equilibrium condition, what we have to remember, center of mass should be vertical. So if the center of mass becomes vertical from the hanging point vertically downward, then at that point it would be in equilibrium. So I've drawn the diagram somewhere here. So this is the hanging point, and from here at vertical somewhere here center of mass would be. So this length is L, this length also L. Now L length is there, so I can write down its center of mass at L by 2 comma 0. This rod also I can write the center of mass, this part of the rod would be L by 2 comma 0. So according to this coordinate that I have drawn, this coordinate system, this is the center of mass coordinate. Okay, now see B point. B point was how much? L by 4, because it is L by 4 upward. Okay, BC would be how much? That B to C is L by 4. So this is L by 4. OB is how much? L by 4. So what about AB? AB would become how much? 3L by 4, and BC is how much? L by 4. So in this triangle now we can define tan theta easily. So tan theta would be given by BC by AB. BC is L by 4. AB is 3L by 4. So tan theta would come out to be 1 by 3rd. So theta would become tan inverse 1 by 3. Clear? Okay. Okay. So let's see the next question now. So this question is saying that find angular momentum about the bottom. About this bottom point we have to find the angular momentum. The given system is there. So F is given 2t. So if I talk about the torque at this point A, so torque about point A would be given by how much? So force is 2t, and what is the perpendicular distance from this point? R plus small r. Okay, this is tau. So we know that torque is given as rate of change of angular momentum. So tau equals to dl by dt, 2t r plus small r. So what about dl from here? 2t r plus small r into dt. Now I'll integrate both sides. I will get the angular momentum. So angular momentum would be how much? R plus r is a constant outside. T would become t square, and that is our answer. Okay, easy problem. Let's see the next one now. Okay, this question, this is an important one. So we have a cylinder that is rotating with omega naught. Okay, a cylinder rotating with omega naught. We are placing it at the corner like this between two vertical walls. Coefficient of friction between all the surface is mu. So find total number of turns by cylinder before it stops. So that cylinder is rotating in this direction, there would be friction here, there would be friction here. So this friction would create the torque, that torque would create an alpha in opposite direction, and that is how it is going to stop. But before stop it is rotating, so it would cover some angle, and obviously in that, from that we can convert it in number of terms. Okay, so this is the free body diagram. On this end, force in the upward direction would be mu into normal, because it is rotating. Because okay, so contact point is slipping, it means that kinetic friction would act. So mu n1, this is the normal, and at the bottom normal upward is n2, so friction would be how much? Mu n2. Okay, obviously at the corner it is not going anywhere, so center of mass must be at rest. Center of mass is at rest. So if center of mass is at rest, so this force n1 should be equal to mu n2. Okay, n1 equal to mu n2. Now satisfying the vertical equation, so n2 vertical is there, n2, and this vertical is mu n1. So n2 plus mu n1 should together balance out what? The weight component downward mg. Okay, mu n1 plus n2 should balance mg. Now we have two equations from here, n1 equal to mu n2, n2 plus mu n1 equals mg. So solving this one, we can easily get the values of n1 and n2. So we got here n1 and 2. Now let's see angular acceleration alpha. So angular acceleration would be given by torque by inertia, tau equals to I alpha, Newton's second law. Now torque would be how much? So let's see torque about the center. So n1 is passing through the center, n2 is also passing through the center. I have told you, whenever the force passes through the center, whenever the force passes through the point about which we are calculating the torque, its torque would become 0. So torque would be given by mu n1, perpendicular distance from the origin is r, and this would also give the torque, perpendicular distance from the origin is r. So F1 into r, F2 into r, both are in the same direction, both are rotating clockwise, so torque would be added. So mu n1 plus n2 are inertia of this disc would be mr square by 2. Okay, now putting the values mu n1 plus n2, so n1 we have here, n2 we have here, adding them we will get this value. So now it's a further simplification only. So we got the value of alpha. Okay, alpha clear? Everyone, alpha is clear, right? So after alpha we can calculate the theta. So that is a constant acceleration. So theta would become omega naught square by 2 alpha. Which equation? Third equation of motion. S equals to u square by 2a. Okay. So putting these values, we'll get this one. This is the distance. This is the angle. This one will tell you angle it rotates before coming to rest. So number would be given by angle divided by 2 pi, because in one rotation how much angle it covers? 2 pi. So from here we will get this value, and that would be the number of rotations that it makes before stopping. Okay, important question, go through it again. Let's see the next one. So OO dash is the axis. This is the rod which is rotating about this axis with angular velocity omega, tilted at angle theta. So we need the torque of centripetal force about the midpoint. So we need to find the torque of centripetal force about the midpoint C. So C is the midpoint. Okay. So what we will do, at distance x we take an element. This element is rotating, this angle is theta. So this element would rotate something like this. Okay. So it would rotate in a radius, that is, this angle is theta. So radius of rotation would be how much? X sine theta. It is rotating. Okay. Mass dm, we are already familiar with how to write the mass, elemental mass of a uniform rod. So total mass by total length, that is density, into length dx. So dm would be how much? M by L into dx. Now centripetal force. So toward the center force is df. So that df is required to rotate it. So df would be dm omega square r, centripetal force, m omega square r. So here element is dm. So dm omega square r. Now putting the value of dm, everything we will get the value of df. So that is the elemental force required to rotate this element in this radius of x cos x sine theta. So torque, now see this force is there. Okay. So this force creates a torque about the center. This distance is how much? Perpendicular distance here. So it would be x cos theta. So torque basically would be how much? Df into perpendicular distance, force into perpendicular distance. So perpendicular distance here is x cos theta, force is df. So we got the elemental torque. Now if you once you got the elemental torque, putting the value of everything, this is the elemental torque expression. By integrating, see integration of the limit of the integration. This is our central line. So backward how much I will go? L by 2 minus. Forward how much I will go? L by 2 plus. So just putting here one extra thing I have done here is sin theta cos theta is there. So I will divide 2, I will multiply 2. So this one would become sin 2 theta divided by 2. So that's what change I have done here. I have taken here sin 2 theta. So here extra 2 comes. Now after integration, simple. So we'll get this value. So that is the required answer of this problem. Okay. Moving on to the next problem. Okay, no problem. Let's move on. Next question number 6. What it says? So we have a rod here. Okay, a stick here. We are hitting it with this stick. We are hitting this ball. It's a spherical ball. So such that what is happening, you know, when you are hitting it, it gets a velocity forward v naught and angular velocity v naught by 2r. Clear? So see here, V equals to V naught equal to how much from this equation, or we can say that V naught equals to 2 omega r. So V naught is more, so V naught here forward, here omega r is V naught by 2 backward. Okay, at the bottom point we have two velocity, forward is centripetal, sorry, translational V naught, and due to rotational we will get backward omega r. So omega r from here is V naught by 2, so V naught by 2, and forward is what, V naught. So tell me, in this condition, forward velocity V naught, backward velocity V naught by 2, so is it pure rolling or slipping? So it is slipping condition. Pure rolling, I have already told you, the contact point must be at what, rest. Okay, so it is slipping. Clear? Now, so the question is that find the time after which friction stops acting. Okay, so friction stops acting. So why friction acts? Whenever there is an external agent to slide it, to try to slide it, to try to move it, in that case friction would act. But you are hitting it with the rod, right? When you are hitting it, you are kind of providing an impulse, you are giving these velocities, so there is no external torque. So initially it is slipping, yeah, that is okay, it is slipping initially. V naught backward is V naught by 2, so there is a slipping, so there would be a friction. But the moment it starts pure rolling, if it starts pure rolling, then what would happen? Tell me. So if it starts pure rolling, friction would vanish. So actually we need the time when after which it starts what? Pure rolling. Okay, so friction acts when there is an external force. Hitting would provide impulse. Ball would roll without slipping. After some time slipping would stop. So does friction. So friction would also stop. Let's see how we are going to see. So I have drawn the two scenarios here. Okay, so the initially at t equals to 0, that is the case here. Central translational velocity of the center V naught, omega is V naught by 2r. Finally, let's say the central velocity becomes V, omega would become V by r, because V equal to omega r. Now at this point, contact point would be at what? Rest. So pure rolling would start at t naught. Okay, so pure rolling would be starting at t naught. Now let's see, very important, it's a very logical problem here. See, conservation of angular momentum about ground. Okay, we have to conserve the angular momentum. So the question would arise here, sir, angular momentum would be conserved in the absence of any external torque, right? But from here to here there is a friction acting along what direction? Along the backward direction on the ground, or forward direction, because of rotating like this, so friction is acting like this. Okay, yes, that is very true. So why angular momentum would be conserved? See again, angular momentum conservation, about we are talking about what? Ground. So about ground, the friction is lying along the ground. No, this is the friction. So if you talk about angular momentum about this point, friction is passing through the point, so its torque would become what? 0. So even though the friction is present between here to here, it is not providing any external torque. So in the absence of external torque, what I can say? Angular momentum must be what? Conserved. Clear? Initial, final, that is the scenario. Now we are going to conserve. See, with what velocity it is moving? V naught. So linear momentum would be how much? Mv naught into perpendicular distance, r. Mv naught into r. Inertia how much? Inertia about this point how much? It would be how much? 2 by 5 mr square into V naught by 2r. No, inertia not about this point. See, here concept I have written. So inertia about this point, suppose angular momentum about this point you want to calculate of this rotating sphere. So center of mass is moving with mv naught. So you will multiply what? Mv naught into perpendicular distance. But inertia omega you will take about the center only. So about any point you want, this is a NEET question in itself. It's a previous year question of the NEET. So if there is a sphere that is rotating, so what would be its angular momentum about the origin? So angular momentum would be its angular momentum about the center, that is I omega, and then center's angular momentum about origin. So I omega plus mv naught into r. So that is why we are talking about inertia. How much? 2 by 5 mr square, and 2 by 5 mr square moment of inertia is for what? Solid sphere about the central axis, about the central axis. So 2 by 5 mr square. Okay, inertia into omega, omega already given, so I have put here. Now final case, center is moving with what? V. So mv into r plus inertia into omega would be how much? V by r. Now by solving it, we'll get a relation between final velocity and initial velocity. So final velocity becomes how much? 6 by 7 times initial velocity. Final velocity becomes how much? 6 by 7 times initial velocity v naught. Okay, let's move forward then. Now we have done most of the part here. So moving with v naught, backward acceleration mu g. After some time, velocity becomes how much? 6 by 7 v naught. In this range, sliding was happening, right? So which friction would act here? Which friction? Kinetic friction. And kinetic friction only one value, mu into normal. Kinetic friction has only one value, mu into normal, mu into mg. So divided by mass, so that's how we are getting acceleration equal to mu g. And throughout this motion, acceleration would be what? Constant. So we already know acceleration constant, equations of motion valid. So v equal to u plus at will apply. Final velocity we have, initial we have, time, acceleration we have. So time would become this much, v naught by 7 mu g. Getting this? Okay. So go through these questions at least two times. Try to write them on your notes and then revise whenever you want. These are important questions. Okay. So let's see the next question now. Okay, next question says that we have a rod here that is placed in a on a horizontal plane, and from at the top we are hitting it, we are providing it an impulse of j. Impulse is what? Change in momentum. Okay, so j impulse given at the top. Find center of mass velocity after hitting, omega about the center, omega of the center of mass, about the center of mass it would rotate. So omega displacement of center of mass when rod makes one complete rotation. Okay, all parts are important. Clear? Let's see the solution then. So after some time, when the rod gets this impulse, it would have two things. The center would move forward with v, as well as it would rotate also. So it would go something like this, then after something like this, then after something like this it would rotate. Okay, like this. So kind of rotation is happening. Now linear momentum conservation, actually impulse is there, so that would be the change in momentum. So initially momentum was 0, final momentum is what? mv. So that would be j equal to mv. So velocity of the center of mass how much? J by m. Clear or not? Simple part, first part done. Second one, similarly angular momentum. So how much angular momentum, angular impulse you are providing? jl by 2. So this is the angular impulse, that would be the change in angular momentum. So I omega. Yeah, initially there was no omega, so no angular momentum. Finally omega, so I omega. So inertia of the rod about the center is how much? ml square by 12. So we got the angular velocity of the rod also about the center of mass. Omega equals to how much? 6j by ml. Okay, this is also clear. Second part also done. Now third part, displacement of center of mass when rod makes one complete rotation. So rod is rotating with what? Omega. So what about the time period? Time period means time taken to complete one revolution. So time period would be 2 pi by omega. Okay, so time period 2 pi by omega. So here we are getting this value of time period in the final. Okay, time period also clear. Now how much distance the center would move in that? So center is simply moving with v and time is t, so distance would be velocity into time. So distance I have written here, velocity into time. Okay, so velocity into time, after that we will get pi l by 3, and that is our final answer. Got it? All part clear? Simple question. Okay, moving forward to the next question. Question says saying that we have a rod like this, mass m, length l rod attached with two strings hanging like this. Find tension in the string just after one string is cut. So one string we are cutting. So what would happen? What type of like overall we are going to analyze this problem. Okay. Okay. So this is the rod. This side cut, so tension becomes 0. This side is still attached with the string, so tension would be how much? T. Downward mg, and about this end point it would rotate, so let's say angular acceleration of rotation is alpha, and the center at this exact point would have a downward acceleration a. Okay, FBD clear? Now Newton's law, vertical direction, downward force mg, upward force tension, so mg minus tension equals to mass into acceleration ma. Okay, now torque about this point, so torque mg, so tension is passing through this point itself, so tension would not give any torque. Okay, so torque about this point would become mg into this length is l by 2, so mg into l by l. Torque is inertia into alpha. Inertia of the rod about this end is ml square by 3. Alpha is this one. So by combining these two, we'll get the value of acceleration as well as alpha. Got it? Easy. Now put this value of acceleration in the first equation. You will get this relation. From there, we'll get the value of tension also. So tension is how much? Mg by 4. Okay. Moving on towards the next question. Same type of question is there. You just try to go through this question on your own. Okay. First you stop the video, go through the question. Exact answer is there coming is going to come out. So I hope you will be able to do this one. Only different thing that we have done here, no, this end is fixed. This is a kind of hinge, so it would come about this point. This B string is being cut, so it would rotate about this point. So you can see the free body diagram, you can see the solution, but give it a try first. Okay, next question, kind of same question, but here the rod, 1/4 portion of the rod, 1/4 portion L by 4 is hanging on this, is staying on this surface, and then we are cutting this string. So free body diagram we have drawn. At from the center, downward force would be mg. It would rotate about this point. First it would tip off, no, it would rotate about this hinge point C, corner point, right? When this string is cut, it would try to fall about this point. Okay, then so normal at that point would be upward, mg downward. So in this one you can directly calculate the torque about this point, about point C. So torque equals to inertia into alpha. So torque inertia into alpha. Achha, torque about this point, force is mg and this length is L by 4. So mg into L by 4. So again, why the normal is not giving the torque? Because the normal is passing through the point of suspension, point of rotation. Clear? So that's why the normal would not give any torque. So we got from here we got the value of alpha. Now see acceleration of the center of mass. So this is the center of mass. This one is rotating about this point with alpha. So how much distance you are moving? L by 4. So acceleration is alpha into distance, alpha into L by 4. Okay, alpha into L by 4. So we got the acceleration of the center of mass also. Now putting this equation, now making this equation in vertical direction, mg downward normal upward, mg minus normal equals to mass into acceleration of center, acceleration of center. So normal would be 4 mg by 7. Okay, so let's see the next question. So the question says that we have a disk, mass m, radius r, which has been placed on the plank. The mass of the plank is m. This plank is placed on the ground, which is smooth, and the plank is being further pulled by the force F forward. So the question is friction force acting on the disc. What is the friction force acting on the disc? And angular acceleration of the disc, alpha for the disc. Condition is there that this disc is rotating without slipping. Okay, it's a pure rotation, pure rolling, rotating without slipping, so pure rolling. Free body diagram. Forward A I have assumed, upward obviously normal, downward mg, and see it is being pulled forward, the plank is being pulled forward, so friction would act backward F. So Newton's third law, friction would act forward on this one. Okay, now this normal was applied by the plank, so on the plank also there is a normal, and then gravity mg, so the ground is there, so it would give the N1 reaction. So N1 reaction is from the ground, normal because of this one, plank because of this disc, and mg gravitational force, weight. So assuming that the plank is moving forward with what acceleration? A1, very important. Here two accelerations I have assumed different. Okay, so this one is moving with A acceleration and the plank here is moving with A1. Now for the plank, forward force F, backward force friction, net force F minus small f. So net force is mass into acceleration, ma1, equation number 1. Disc, forward force friction F, so F equals to mass into acceleration A, equation number 2. And for the disc we can write down the torque about the center. So torque would be, see here, friction is F and perpendicular distance is R. So how much torque in the backward direction? F into R. So F into R. So torque would be inertia into alpha, Newton's law. Inertia of the disc how much? Inertia of the disc is mr square by 2. Okay, mr square by 2 into alpha. Okay, now see, this disc is moving forward with A acceleration, center of mass, not the disc but the center of mass of the disc, moving forward with A acceleration, and it is rotating backward with what? Alpha. So tell me, if it at this point what would be the total acceleration? So forward acceleration A, translation, so translational acceleration A, but because of rotation there would be a rotational acceleration, so at this point tangentially forward, and that would be R into alpha. So net acceleration of this point is what? A plus R alpha, and the plank is having how much? A1 acceleration, right? Now tell me, they should not slip, this one sphere should not slip on the plank, so their contact point must be at what? Rest. Contact point must be at rest means A1 acceleration must be equal to what? A plus R alpha. Okay, so A1 acceleration equals to A plus R alpha. Now we have A1 from this equation number 1, capital F minus small f by capital M equal to A from this one, F by M, alpha from this equation 2F by M. So by doing simplification, where is our simplification? So it further simplifies to this value. So friction force would be this one, and from this friction we can calculate the alpha value also. So that would be the value of alpha. Okay, important question. Every step here that I am doing now, you have to go through it again. So what you do, once you see the video, after that take the question and try to solve it on your own. Then only you will understand the tactical things that at different steps I am doing. Just by seeing the video, you are not going to learn that. You have to practice it on your own. Okay.